Hello YouTube. Today we introduce new topic for discussion that will be electrical capacitance and a parallel plate capacitor. So hello YouTube. Today we introduce a new topic for our discussion. This will be electrical capacitance and capacitance of a parallel plate capacitor as an example. So we will introduce these concepts and we'll make a very simple pencil drawn electrical parallel plate capacitor and carry out some measurements of its capacitance. So let's start from introducing the concept of electrical capacitance. So let's assume that there is some isolated conductor or a system of two conductors placed close to each other. So the charge which such system can collect on its surface will be proportional to potential difference between two conductors if we are talking about a capacitor, because capacitor is a system of two conductors. It can be of different configuration. The most common is parallel plate capacitor when we have two parallel plates as conductors. And here we need to multiply it by some proportionality coefficient, which is electrical capacitance. So units for capacitance are farads, and that's quite large magnitude. So usually we operate with picofarads, nanofarads, microfarads, and so on. So now let us introduce a system of two parallel plate conductors, which is a parallel plate capacitor. So we consider it in a cross section. So this is one plate, this is another plate. So let us assume that these plates are charged. So they possess some charge Q plus and some charge Q minus. So these charges are equal in magnitude and obviously opposite in the sign. So when we have positive electric charge at some plate, it will create uniform electric field perpendicular to the surface of this plate. So now it is important to mention that we place these plates at some distance d, and this distance is much smaller than the linear size of the parallel plate capacitors, in order to have uniform electric field distribution in between these two plates. So now we have positive charge at the left plate, and we can draw electric field lines. So we have electric field created by positively charged plate. So here it will go in outside of this space between two plates also. And now we need to represent electric field created by negatively charged plate. So this is negative charge, means that electric field lines will terminate on this negatively charged surface. So that's why we can draw these electric field lines in this manner. So they will terminate on the surface of negatively charged plate of the capacitor. So now we introduce equation which gives us electric magnitude of electric field created by charged parallel plate with very large dimensions. So that will be sigma divided by 2 times epsilon naught. So sigma here is surface density of electric charge, and that will be given as total electric charge divided by area of the plate. So we assume that this area of the plate is very large, approaching to infinity. So we have some uniform distribution of electric charge over this plate. So now let us look at this schematics, and we will see that electric fields created by positively charged plate and negatively charged plate, they have the same direction inside the space between these two parallel plates. So what it means that our electric field net electric field will be twice larger than it would be with just a single plate. So that's why let's denote this as E naught. So electric field inside E naught, net electric field inside the space between two capacitors will be equal to sigma divided by epsilon naught. So epsilon is the electric constant of material which fills this space inside the capacitor. It could be air, then epsilon is equal to unity or vacuum. However, it could be some dielectric material with different dielectric constant. Dielectric constant defines how much weaker electric field is inside given material, dielectric material, in comparison to vacuum, free space. So, and this is dielectric epsilon naught, it's a dielectric constant of free space, like it's a universal constant. So now we have electric field, and that's very important to underline, uniform electric field in between these two plates, which is E naught, its magnitude. Uniform means that in, let's put here x is x, it doesn't change its magnitude as we go from 0 to d, which is thickness of the parallel plate capacitor, means the width of the gap between two plates. So this electric field is uniform, and the reason why we specify that this distance d between two plates should be much smaller than the linear size of the plates, that's assumption gives us quite valid reasons to make such a statement that we have uniform electric field in between these two plates. So now let us define what will be potential difference delta V between these two plates. So delta V is nothing else as electric field, which in our case uniform electric field, times d, which is distance between two plates. And now we can write that this will be equal to Q, total charge accumulated at the plate, times d divided by epsilon naught, and divided by area A. So we just reproduced this equation by substituting instead of sigma Q divided by area, and then instead of E naught, we substituted expression for E naught, which we shown previously. So now we have expression for potential difference, and we are approaching to the step when it's possible to introduce capacitance of this parallel plate capacitor. C capacitance will be equal to total charge accumulated Q divided by delta V. So now we have Q divided by Q times D, and that is divided by epsilon naught times A. So now, after rearrangement and cancelling the total charge, we will get the final expression epsilon naught times A divided by D. So this is a well-known expression for capacitance of a parallel plate capacitor. So let us discuss this a little bit. And here we see that the amount of electric charge, which like Q, which is accumulated by capacitor, is not in this equation. So capacitance does not depend on amount of electric charge, which is already accumulated. Which parameters really define capacitance? So this is constant, epsilon naught. So we have three parameters: epsilon, area, and distance between two plates. Epsilon, the electric constant, so the larger the electric constant, the larger capacitance will be. Means if we have free space or air in between two plates and we fill it with some dielectric material which possesses larger dielectric constant, then capacitance will increase. Okay, so now area kind of makes sense. If we increase area of these plates, we have larger active area, larger size of this parallel plate capacitor, and capacitance increases. So here is thickness. So this thickness is not so straightforward. Why capacitance decreases as we increase thickness? Because we could consider, okay, we increase thickness, and between these two plates, thickness D, and the volume, which is defined by this parallel plate capacitor, will increase. So why capacitance decreases? So the thing is that magnitude of electric field, which is uniform in between these two plates, does not depend on distance between two plates of this capacitor. And then voltage drop, delta V, or potential difference between two plates, is defined as product of some constant which is independent on thickness times like thickness or distance between two, thickness of the electric layer, or in other words, distance between two plates of this capacitor. So that means that if we increase thickness, this guy stays the same, electric field inside the parallel plate capacitor, uniform electric field magnitude will remain the same, and only distance between parallel plates increases. So in that case, this potential difference between two plates will increase. So since it is in denominator for this expression of capacitance with the same amount of electric charge accumulated by this capacitor, as we increase distance between two plates, potential difference increases, and that causes drop in capacitance. That's why we have this distance between two plates in the denominator, and as we increase distance between two plates, capacitance goes down. So that is very general introduction of capacitance of a parallel plate capacitor, and the key message here that capacitance of this capacitor will depend exclusively on two factors: material of the dielectric we use, epsilon, and the electric constant of this material to be more specific, and its geometric factor, area and distance in this case, or some other geometric factors if we are talking about capacitors different from parallel plate capacitors. For instance, some spherical capacitor or coaxial capacitor. That is going beyond our discussion here. We focus on the most common and important for understanding type of capacitors, which is parallel plate capacitor. So now, after this short and important discussion, we can make some demonstration for making and measuring a parallel plate capacitor. So for this purpose, we will use a soft graphite pencil. Regular pencil can be applied soft just because we have less clay and more graphite powder in the lead of this capacitor. So we will use this guy. Let me maybe clean first this part. And for our reference, we can maybe write that capacitance, like final equation which we derived, epsilon naught times area divided by d. Okay, so we will use this so-called magic tape as our insulator layer, the electric layer between two plates. And plates, as you might already guess from the title of the video, it will be drawn on the some cardboard or piece of paper, whatever you want, with this soft graphite pencil. So how do we start here? We just draw some, like define some area where will be our first plate of a parallel plate capacitor, and start to draw this area. Quite simple activity. Almost like in childhood. So what's the purpose of this activity? We are drawing an electrode, quite parallel electrode, because this is a flat surface. So graphite is a good conductor, and it's kind of a semi-metal, more metal than anything else. But because of layered structure of graphite, we can easily layer by layer deposit it on some rough surfaces, which is, for instance, paper. So that's why we make such a nice film, which will be electrically conductive. So technically, this is already an electronic device. It's a resistor. So we can demonstrate this with a multimeter, and for this purpose we will measure resistance. Here should be resistance, and let me change choose the right position. So let's check. Yeah, short circuit. So now we put these terminals of the multimeter and would on the surface of graphite film. So what we see, kind of around 10 kilo ohm. So yeah, obviously if we put them further from each other, resistance will increase. So we have 17 kilo ohm. If we can place them closer, will be smaller resistance, 8 kilo ohm. So clear demonstration that this is a conductive film. Obviously it's not very conductive because 8 or 10 kilo ohm is quite high resistance. However, it is good for demonstration of the parallel plate capacitor, because we don't require here very high conductivity. So now we have one electrode on this card, and we can deposit, in parentheses, deposit the dielectric layer. So scissors. So this is our dielectric layer. Let's place it over our electrode. Okay, so now we have the electric layer on top of first electrode, and since this is kind of magic tape, it has rough surface, we can draw with a pencil on top of this tape. So we need to be careful not to short the two plates, so we should have some distance between edge of the tape to start where we start drawing second electrode, and that is where, and also up to this edge we should not go beyond it, otherwise we will short. So this is our outline of the top electrode, so they are oriented one over another, overlap, and now we can draw this area inside the frame which we outlined here. I'm using soft graphite pencil. It's easier to draw like thicker, like deposit thicker graphite films, but any graphite pencil will work for this purpose. Okay, so let us check resistance of this top electrode, which is drawn on tape. Okay, we have similar 10. Oh no, that's actually 10 meha ohm. So here somehow, because of the different morphology of this tape, we cannot deposit as thick graphite film, so resistance is quite high, it's 25 meha ohm. So let us try to draw a bit more in the perpendicular direction, so maybe we can increase a little bit the thickness of this graphite layer, or at least improve its uniformity so we can get better conductivity. It's still fine. We don't need very conductive film for this application. Just needs to be able to conduct electric current, and that is already demonstrated, but let's try to make it a little bit thicker as much as we can. So the most important, not to go too far to the edges so we don't short the bottom and top electrodes. So now what we will do, we will use different instrument, which is LCR meter. And here is our pencil drawn capacitor with tape, scotch tape in between as an insulator layer. We can contact to the bottom electrode. So now you see it shows at the level of noise like 3.6 picofarad. This is 1 kilohertz frequency for the measurement. That's very important to specify frequency at which any capacitance or other like inductance is measured. So we contact one electrode and we contact the second electrode. Okay, so now we see this is our capacitance. So we have 100 picofarad capacitance of this parallel plate capacitor, which we just made with very simple materials and technique. I'm sure you will have some other ideas how to make parallel plate capacitor, but I find this approach quite entertaining and educational. So if we disconnect, so you see we come back to the background noise level with a capacitance of just these cables, 2 picofarad. So now we contact it again and we get to 100 picofarad. So phase shift between current and voltage minus 81, which shows that we are close to minus 90 pure capacitance. If we're lower frequency, probably it would be even closer to 90 degrees. But these questions we will discuss somehow in the future. So that was my purpose of the video, to introduce concept of electrical capacitance, discuss parallel plate capacitor as the most important representative of capacitors, and fabricate and measure very simple pencil drawn parallel plate capacitor for demonstrational purpose, and probably in this case a bit of entertaining purpose too. Thank you for your attention. See you next time. Bye.